hiss, Kayvon can work out the size of the star. In this case, it's around the same size as our star, the Sun. Kayvon's work could be the breakthrough exoplanet hunters have been hoping for. It's cheap, the results are practically instantaneous, and once you know the size of the star, figuring out the size of the planet, casting shadows over it, is child's play.
It feels like a very privileged time to be a scientist, to be an astronomer working in this area and contributing to the hunt for the next Earth. Here we are actually discovering these worlds by the hundreds, and now on the cusp of being able to identify the next Earth.
Astronomers suspect there could be tens of billions of rocky, Earth-like planets in the Milky Way. Places where perhaps life has gotten a foothold. But life as we know it requires water. How can scientists possibly find this miracle substance on planets light years away? Water divides our living world. Those with it prosper. Those without suffer. Remarkably, the water we drink today contains the same atoms as the water dinosaurs drank 100 million years ago. It's the same water that formed clouds over the early Earth 4 billion years ago. And every organism that has ever existed on Earth has used this single ration of water as the biochemical powerhouse that keeps it alive.
On Earth, all life requires liquid water to grow and reproduce. It's the common ecological requirement for life.
Liquid water is just so good for getting evolution going. Molecules can dissolve in the water, actually interact with each other, form more complex chains.
It does it with charge. There's positive charges and negative charges separated between the hydrogen and the oxygen in H2O. Those charges break apart the hydrocarbons, the carbon-based molecules that persist everywhere in nature.
Now that's very rare. Hardly any other liquids do that. So liquid water is a natural starting place when you look out into the universe and say, what planets could possibly have life?
To understand how much liquid water is out there, astronomers must first calculate how common water is in all its forms. Amazingly, they find it everywhere they look.
Water is incredibly common. In its gaseous form, we see water vapor filling the space between the stars. We see it in clouds of material that are actually forming new stars and planets right now.
Since water is a fundamental building block of stars and planets, exoplanet worlds must surely have it in abundance. But if you're looking for life, you need to find liquid water, and plenty of it. To find it, astronomers take their cue from a fairy tale.
Everybody knows the famous story of Goldilocks and the Three Bears and the cup of porridge, where one was too hot, one was too cold, one was just right. When it comes to cooking up life like a porridge, you need to have an environment that's not too hot, not too cold, just right. And traditionally, we look for that at a certain distance around a star.
At first, astronomers based this magical distance, known as the Goldilocks zone, on the Earth's orbit around the Sun. But as they found more and more exoplanets, they've had to reevaluate the boundaries for liquid water.
There isn't a single distance. It depends on the brightness of your parent star. A dim star, you need to be closer. A hot star, very bright, you need to be farther away.
Scientists have calculated just how many rocky planets may lie within the Goldilocks zone of their stars. It comes out to over 30 billion potentially watery worlds. Even more remarkably, recent discoveries have shown us it's not just planets that can bask in the warmth of the Goldilocks zone. There may be moons, bright blue with oceans, too.
Most of the planets we're finding are big Jupiter-sized planets. However, a lot of them are orbiting roughly where the Earth is orbiting the Sun. So even if the planet that we're finding can't support life, it could have a moon with an atmosphere that could support life.
And the biggest of these rocky moons may resemble our home.
There could be billions upon billions of exomoons out there, and even perhaps countless paradises teeming with life.
David Kipping searches for exomoons by looking for double dips in the brightness of distant stars.
We look for exomoons in a very similar way to the way that we look for planets, by looking for them transit their host star. Now, if that planet had a moon, then we should expect to have one big dip due to the planet, and then one smaller dip either to the left or to the right due to the moon.
Habitable exomoons may play host to one of the most spectacular sights in the universe. Imagine a warm, rocky world, just like our own, with oceans and mountains. But in the sky, a massive ringed planet with a fiery sister moon shooting hot magma into space. Exoplanets, and now the vast potential of exomoons, hint at a galaxy filled with the possibilities for life. But a rocky surface